Hi, Chem 101 students. Welcome back. It's week 11, and this week we're going to be talking about the shapes of molecules. But before we can do that, we need to be able to represent the molecule on a piece of paper to keep track of which atom is bonded to which other atom and the way in which those bonds are arranged. So I'm going to be talking about a concept called Lewis structures. Now, we did slightly introduce the idea of Lewis structures for ionic compounds when I was teaching you how to name ionic compounds. I think it's useful to show those at that time. Your textbook does begin to show you Lewis structures for ionic compounds in this chapter, although they're significantly less important than Lewis structures for covalent compounds, because covalent compounds make molecules, and molecules have particular shapes, and we're going to use those Lewis structures to figure out the shapes. So key to determining the Lewis structures will be counting the valence electrons between all the atoms. The valence electrons are the electrons that participate in bonding, so we need to know how many of them there will be. We will also talk about an idea called covalence number, which isn't really talked about much in your book, but I find it to be an easy way to organize your thoughts when you're making a Lewis structure, so I'll be introducing that idea. It just helps you to draw the Lewis structures easier. And then we'll go into the center of the way bonding works. It is the octet rule. So you guys are already familiar by now that bonding tends to happen in such a way that each atom has a full 8 valence electrons around it. And so that is going to be called the octet rule. And we're going to make sure that when we're drawing Lewis structures that all of the atoms are obeying the octet rule. So back when we talked about ionic compounds, we talked about how to write a Lewis dot structure for ionic compounds. In the ionic compound, the metal gives up all of its valence electrons to make a positive ion. So you can see here we had the metal sodium ion with its positive 1 charge. The nonmetal will grab more electrons until it has 8, and that is represented by the 8 dots in the square, the dots representing valence electrons here. And because the non-metal atom gains electrons, it becomes a negative ion. And we separate the dots from the charge by using a bracket here. For covalent bonding, electrons don't move from one atom to another. Instead, they are shared. And so we talked about that back when we were talking about how to name covalent compounds. So for example, here, hydrogen has 1 valence electron because it's in group 1. Fluorine has 7 valence electrons because it's in group 7. But if they each share an electron, hydrogen will have 2 electrons around it, these white ones here, and the fluorine will have 8 electrons around it, the 6 that are blue and the 2 that are white here. And so a covalent bond involves the sharing of electrons. And for that reason, the way that covalent bonds are arranged in three-dimensional space is very different. It's a very different type of bonding from ionic bonding. And so we've talked about how that results in different types of properties, which we'll go more into in the next chapter. But mainly, we want to know something about the way these electrons are shared and the directions to which those electrons are shared around an atom that is bonding to other atoms. And that's what writing the Lewis structure is going to be about. So when we draw a Lewis structure, you're going to want to follow 5 steps. And often my students just want to start, they see the formula for which they want the molecule they want to write the Lewis structure for, and they just hit the ground running and start drawing things. You don't want to do that. That's the way you get these wrong. If you do it this way, it actually becomes quite difficult to get it wrong. And you can always check at the end, which I'll teach you how to do. And if your checks work out, you will know that your answer is right. You won't even need me to tell you that it's right. You will know it's right. Okay, so what are these steps we're going to do? Step 1 is we're going to have to count up all the valence electrons. And remember from the previous chapters, the valence electron for an atom is the same as the group number that it's in. So we can determine the number of valence electrons simply by looking at the periodic table and looking for the group number. Step 2, we want to determine the covalence number. And so the covalence number is the number of bonds that this atom is most likely to make. And so each type of atom has a different number of bonds that it will usually make. And that's what we're going to try to identify with the covalence number. Next, you will draw a skeleton structure where you draw the arrangements between the bonds of the atoms. Which atom is bonded to what other atom? And we're going to put the atom with the highest covalence number in the middle on the skeleton. Step 4, we're going to put the remaining valence electrons as lone pairs, and we'll talk about what lone pairs are, around the atoms until each has an octet, or 8 electrons around it. We'll do the outside atoms first and the center atoms last. There is one exception to the octet rule. It's hydrogen. I'll go back to the last slide in a moment, and you'll notice hydrogen only had 2 electrons next to it. It's because hydrogen is in the first row. It only has the first shell to fill, and so it's special because it only needs 2 electrons to fill its first shell. The rest of the atoms are going to need 8. Finally, step 5 is only done if you run out of valence electrons before all atoms have an octet. At that point, you don't have enough valence electrons to give all atoms an octet without making what are known as double or triple bonds. And in a bond, generally 2 electrons are shared in a covalent bond. But in a double or triple bond, more electrons will be shared in order to make that bond. And it results in a stronger bond. So you can see here, looking back at our example, there are 2 electrons shared. Fluorine is obeying the octet rule. These are lone pairs right here. And these electrons are in the bond. So 2 electrons being shared make the bond. And again, hydrogen is special. It doesn't need 8, it only needs 2. So that's why you only have those 2 around the hydrogen. But you have 8 around fluorine and all other atoms. Okay, so the best way to show how to do this is just with a series of examples. So let's start with an example. And the very first step is going to be the most important step. The covalent bonds are formed using the valence electrons of the atoms. So it's very, very important that you know how many valence electrons you have. This first step, I put it big and bold because you do not skip this step. Do not skip. A lot of people want to skip this first step. I'm telling you, that's the easiest way to get the question wrong. Do not skip the first step. Okay, so let's perform that. Let's say we want to write the Lewis structure for the molecule SF2, sulfur difluoride. So what we're going to first have to do is count up the valence electrons in our atoms. We're going to want to go and open up a periodic table. So mine is right here, the same periodic table you guys use. And we're going to identify the atoms in our the atoms in our molecule here. Remember that the valence electrons are given by the group number, where the group number is the ones in Roman numerals here with the A. So our group numbers here are going to be like this: 1, 2, and then 3, like 3A here. 4, 5, 6, 7, 8. Okay, so we had in our SF2, we have a sulfur, so that's going to have 6 valence electrons, and so our molecule is SF2, and we're going to have fluorine, so each of those fluorines will have 7 valence electrons. Okay, so we have 1 sulfur, we know because there's a 1 subscript, not written here because 1 isn't written, and it has 6 valence electrons because it's in group 6. We're going to have 2 fluorines, and each of those fluorines will have 7 valence electrons because fluorine is in group 7. Okay, so now we multiply the number of valence electrons for each atom times the number of that kind of atom that we have in the molecule. We have 1 sulfur atom. It has 6 valence electrons, so 1 times 6 is 6 valence electrons here. We've got 2 fluorines. Each one has 7 valence electrons, so 2 times 7 is 14. At this point, we add up all of our valence electrons all together. So we have 6 plus 14, that adds up to 20. So we've got 20 total valence electrons. That is the first step, to count the valence electrons. Do not skip that step. Please don't skip that step. You must do this step. Otherwise, you won't know when you've run out of valence electrons. You won't know when to make a double bond or a triple bond. You won't know really what to do at all. You need to count the valence electrons. Please do that first, every time. So sulfur difluoride has 20 valence electrons, and so now we can move on to step 2. So step 2 is determining the covalence number, or the number of bonds that a particular type of atom prefers. So most of the time, like 95% of the time, an element will form the same number of bonds almost all the time. There are lots of exceptions. In fact, your textbook is going to go into all kinds of exceptions. Exceptions to the octet rule, exceptions to the number of bonds. It's going to go into all kinds of exceptions. I'm not going to really go into those exceptions. If you want to learn more about those, you can read those parts of the textbook, or you can take the next chemistry class, Chem 150. It will certainly go over all those exceptions. I'm going to focus on the types of atoms that are involved in biology, and generally in biology, they do make this number of bonds that is focused on a covalence number. If you're going into the physical sciences, you'll learn more about this. So covalence numbers. What are the covalence numbers? So the covalence numbers are actually the number of electrons that an atom needs to fill up its valence shell. That's 2 for hydrogen, 8 for every other atom. So it depends on how many electrons they're starting with. For example, for covalence number for hydrogen, it's always 1. Hydrogen only makes 1 bond. It can't have any more than 2 electrons. So hydrogen's a special case. Now, the other ones are fluorine, bromine, chlorine, bromine, and iodine. Those are all in group 7. So those start with 7 valence electrons. In order to have 8, they need 1 more. And the way they get the 1 more is by making 1 bond, and they share an electron with another atom, and then they have 8. And so that's why all of these elements that are in group 7, they want to only make 1 bond, because they only need 1 more electron to have 8. So you don't really need to memorize what I've written here, that the covalence number, you don't have to memorize that the covalence number is 1 for fluorine, chromium, bromine, and iodine. All you have to do is have your periodic table and understand that when these atoms make bonds, they make bonds so that they can get 8 electrons. Since they already have 7, they only need to make 1 bond to have 8. They will share that electron with another atom. For oxygen, sulfur, and selenium, these nonmetal atoms, they will make 2 bonds. Because they start with 6 valence electrons, they need 2 more to have 8. So they will make 2 bonds in order to get those additional 2 electrons. For nitrogen and phosphorus, they tend to make 3 bonds. Their covalence number is 3. This is because they start with 5 valence electrons. They need 3 more to have 8, so they make 3 bonds in order to get 3 more electrons, 1 from each bond that they get by sharing with another atom. Finally, carbon and silicon make 4 bonds. Again, they start with 4 valence electrons, they need 4 more to have 8, they make 4 bonds. So these covalence numbers aren't something you should really memorize. You should be able to infer them from the periodic table. And for hydrogen, hydrogen is a special case again because hydrogen, it has only the first shell, and to fill up the first shell it only takes 2 electrons. So hydrogen is special, it always has 2 electrons. It never has any more as lone pairs or anything, and it only just makes its 1 bond every time. So let's now assign covalence numbers for sulfur and fluorine. Sulfur is in group 6. It would need 2 more electrons to have 8, so its covalence number is going to be 2. Now fluorine is group 7, so each fluorine atom has 7 valence electrons, so each fluorine atom we'll need one more to have 8. So each fluorine atom is going to want to make one bond. So now we have our covalence numbers. And it's a very good idea when we're going into the next steps to look at the covalence numbers and let those guide the way you draw your skeleton and place your bonds, because the covalence numbers tells you how many bonds this atom is probably going to make. So it's a good guide to when you're drawing your skeleton, to tell you how many bonds should be going to each atom. Since sulfur wants the most bonds, it wants 2 bonds, when we draw our skeleton, we're going to be putting sulfur in the center. So that's step 3. Draw a skeleton structure with the highest covalence number atom being in the middle. And so when we draw this skeleton structure, we're going to put sulfur in the middle, and we'll put the fluorine atoms around it. So the way we're going to draw a bond is with a line like this. And this line represents 2 electrons. So the other way to write it would be like this. If we did it like we did before with the dots, it would be like that. Each bond represents 2 electrons, but this is the preferred way to write it. You don't want to write it this way anymore. You want to write it this way. This is the right way to write it from now on. So just remember that each line that is a bond represents 2 valence electrons. So we've written this skeleton structure. It's right here. Okay. And we put sulfur atom in the middle because it had the highest covalence numbers. Again, 2 electrons that are shared to form a covalent bond. They're represented by a line like this. And all atoms must be in here. So our molecule was SF2, right? SF2. So we must have 1 sulfur atom and 2 fluorine atoms, which we do have. And so now we have a valid skeleton structure. So we're done with step 3. The next step is going to be to now drop lone pairs on the outside atoms. Sulfur here. Sulfur is in the center because it has a higher covalence number. Kind of wrote over that. I should have put that here. So step 4. We're now in step 4. Now we've drawn our skeleton and put the highest covalence number atom in the middle. We're going to put the remaining valence electrons on the outside atoms as lone pairs until each atom has an octet. So we got this structure here, and I'm just going to copy it down here so I can go with you or show this to you along the way. So I should put it somewhere else. I'm going to put it right above it. So here's our structure we had. Now we're going to put lone pairs on the outside atoms first. So I'm going to put 2 electrons here, and I want to do it till they have 8. So this is 2 electrons. This lone pair is another 2 electrons. So we got 4 here. We've got 6, and we've got 8. Okay, so 2, 4, 6, and 8. So the fluorine has an octet. And now we're going to do it on this other outside atom. And now this fluorine has 8. 2, 4, 6, and 8. So each atom must have 8 electrons around it except for hydrogen, which only has 1 bond. And the pairs of dots are called lone pairs. We do the outside atoms first and then the center, just like we did here. And so now we've got electrons on the outside atoms. And so fluorine has 2 electrons from 1 bond. It needs 6 more, so we put the 6 as dots there. Now, finally, we're going to put the last 2 on the middle, and it will look like this. So each atom must have 8 around it, where the pair of dots are called lone pairs again. Same thing as we were saying last time. The sulfur now has 4 electrons. My arrow is a little off here. Let me put that there. And so going back, okay, so before we saw this final answer here, we had this. And it's always a good idea to double check that you haven't passed your set number of valence electrons. So back from our table, we had 20 valence electrons available. How many do we have now? 2, 4, 6, 8, 10, 12, 14, 16. We have 16 placed. And so we've used up 16 of our valence electrons. So now we have 4 valence electrons left. And that's why we're going to put them now on the sulfur. And so we do. And then we get that final structure that we see here. And then now that we're all done, we can count that everything has worked out okay. So let's look at this. Is this the correct structure? We're going to count all of the dots here. So 2, 4, 6, 8, 10, 12, 14, 16. 16 from the dots. Okay. Then we got 2 bonds. 2 in each of these, so that's 2 and that's 4. 4 altogether. So we had on our chart that we should have 20 valence electrons, and that is what we have. So we've checked our number of valence electrons now. So that is correct. 20 valence electrons, just like we counted up at the beginning. And then finally, we should check covalence number. Each atom will have a number of bonds equal to its covalent number in Chem 101. However, in later classes, if you take more chemistry, this won't always be the case, but for my class, it will be. So we should check, are the covalence number rules being obeyed? Well, the covalence number rule was that fluorine should make 1 bond, and each fluorine is making 1 bond. And sulfur should make 2 bonds, and the sulfur is making 2 bonds. And so our covalence number rules fit here. Finally, does each atom have an octet? Okay, well, we have 2, 4, 6, 8 around this fluorine, 2, 4, 6, 8 around this fluorine, and then finally 2, 4, 6, 8 around this sulfur. So when we have checked now the total number of valence electrons, that checked. We checked the covalence number, that checked, and we checked that they all obeyed the octet rule. If you check those 3 things and they all check out, you're right. You know you're right. You don't even you don't need me to tell you you're right. You are right. Okay? So that's one of the great things about these kinds of problems, is that it's relatively simple to check that the structure you drew is correct. Okay? And that is true even if there's more than one possible answer. For some larger structures, it's possible that there's more than one way to write these. However, if the way you wrote it obeys all of these, valence electrons, total valence electrons, covalence numbers, and octet rule, you are right, period. Okay. So that's pretty great. Sulfur has 8, and each of the fluorines has 8, 6 from the lone pairs, 2 from the bonds. We are good. So in our last example, we had 20 valence electrons available, and between the bonds and the lone pairs, we put 20 down. We had exactly enough to give everyone an octet. But for step 5, we will apply this when we don't have enough electrons to go around. So we will only use step 5 when there are not enough electrons to give all atoms an octet. If there are not enough, then we will share the electrons in more than a single bond. So we will make what's known as a double bond, where instead of sharing 2 electrons to make the bond, 4 electrons are shared. So an example of a molecule that contains a double bond is formaldehyde, CH2O. And so let's follow our 5 steps here. Remember, we're going to follow these 5 steps every time. The way you get yourself into trouble is not following these 5 steps. Make sure you follow them. Step 1, count our valence electrons. So we've got in this one here, we've got, now we don't have sulfur and fluorine. What we're doing this time is CH2O. So we've got a carbon, we've got hydrogen, two hydrogens actually, and we've got an oxygen. So the carbon is going to have 4 valence electrons. Whoops. Carbon has 4 valence electrons. So we've got one carbon, and that carbon has 4 valence electrons. We've got 2 hydrogens, and each hydrogen is going to have 1 valence electron, group 1. Oops. And so by the way, 1 carbon times 4 electrons. So the carbon has 4, we have 4 valence electrons from the carbon. For covalence number is, we look at the group, it's group 4. Each carbon atom would need 4 more electrons to have 8. So carbon's covalence number is 4. Next, let's do the hydrogen. We have 2 hydrogen atoms, and each hydrogen atom has 1 valence electron. We have 2 hydrogen atoms times 1 valence electron for each hydrogen atom. That is going to be 2 valence electrons for the hydrogen atom. Covalence number for hydrogen is always 1. Because remember, all of these, they want 8. But hydrogen's special. It gets full with 2 electrons. So it starts with 1. It only needs 1 more to have 8. So the covalence number for hydrogen, always 1. Okay, next we've got oxygen. 1 oxygen, since there's no subscript written here. 1 oxygen, and each oxygen has 6 valence electrons. So we have 1 oxygen, 6 valence electrons. We have 1 of these, and it has 6, so we get a total of 6 valence electrons from the oxygen. For the covalence number, oxygen starts with 6 valence electrons. It would need 2 more to have 8, and so it will have a covalence number of 2. Okay, so now we've done step 1, count the valence electrons, and we've done step 2, we've determined the covalence number. Now we're ready to move to step 3. We can draw a skeleton structure. Oh yeah, sorry, I had to add the valence electrons. I didn't do that. 4 plus 2 is 6, plus 6 more is 12. Okay, now we're ready to go. Step 3. So for step 3, we want to draw the skeleton, and we make sure that our element with the highest covalence number is in the middle. The highest covalence number is 4, so that means carbon's going to go in the middle. And so we'll draw carbon in the middle here. So carbon. Okay. And then we want to fix that. Okay. Now we want to attach the other atoms to it. The direction you attach them doesn't matter. I'm just going to happen to put oxygen here. I'll put hydrogen here. I'll put hydrogen here. And I'm doing this because I happen to know the way these atoms are arranged, but we actually use the Lewis structure to figure that out. So I had 2 hydrogens, so I attached 2 hydrogens to my center atom, the carbon. And I have 1 oxygen, so I attach 1 oxygen atom to my center atom, the carbon, and that's my skeleton structure. Now notice, down here on the slide, I drew it with the oxygen atom facing down. I also drew it with the hydrogens at slightly different angles. That doesn't matter, okay? The real molecules, they're flipping upside down all the time, and they're wiggling around, okay? So, and besides, the Lewis structure is not a real molecule. It's a way to keep track of the bonds by drawing things on a flat piece of paper. But real molecules are 3-dimensional objects with their own shapes. And so it doesn't matter if I draw it like this or if I draw it like this. Either way is okay. Because the reason why the skeleton structure is okay is because in both cases the carbon is in the middle. And in both cases, the carbon has two hydrogens bonded to it, and it has two oxygens and one oxygen bonded to it. So this skeleton structure is exactly the same as this one. They both achieve the same purpose. The way in which we orient these does not matter. What matters is the carbon is attached to two hydrogens and one oxygen. Okay, so now we're done with step 3. We have drawn a skeleton structure. And so we have our skeleton structure here. Okay, and next what we're going to do is we're going to put lone pairs on the outside atoms first. So we've done three bonds, by the way. So we've used 6 electrons. So we can just keep track of that. So we started with 12, we used 6, we have 6 left, okay? And so we can put those electrons as lone pairs. We're going to do this on the outside atoms first. And very important is that hydrogen doesn't get any. Hydrogen is special. It can't have more than 2. It already has 2 in this bond. That's it. Everyone else wants 8, but only hydrogen can only take 2. So it's done. So the only outside atom we have left that isn't in the center is the oxygen. So we're going to put 6 electrons as lone pairs on the oxygen. So we're going to do 2 here, and 2 here. 6 more valence electrons give an oxygen octet. 2 here, and 2 more right there. Boom. And so now our oxygen has an octet. And by the way, we used 6 more electrons. So minus 6 again equals 0 left. We use all of our valence electrons. Whoops. Kind of put that behind my head. But we use the last 6 right here. That's what I mean. We use the last 6. We use them right here. Okay. All right. And so now we have an issue though. We have no more electrons left. We can count them. 2, 4, 6, 8, 10, 12. We've put down 12 electrons, and that's all we have. But this leaves carbon without an octet. It does not have an octet anymore. It doesn't have an octet at all. That's a problem. Okay, so we're going to have to fix it. And this is where we use step 5. You only use step 5, and you only make double bonds if you've tried to give every atom an octet, but you ran out of electrons, like we did here. We ran out of electrons, and carbon still does not have an octet. And so now what we're going to do is we're going to apply rule 5. What we're going to do is we're going to get rid of one of these. So I'm going to cross this out. So I'm going to get rid of this lone pair right here. I'm going to cross it out, and I'm going to instead make it a second bond. So now we have a double bond, 2 lines. And we now are sharing 4 electrons between this carbon and this oxygen. And at this point, the carbon has an octet. Let's count them up. So let's redraw this now with the double bond, only 2 lone pairs. It's going to look like this right here. Remember, hydrogen is a special case. It doesn't need an octet. So everyone should have an octet now. So to get 4 bonds on carbon and also notice here, there's 4 bonds on carbon, 2, 4, 6, or 1, 2, 3, 4 bonds on the carbon. There's 2 bonds on the oxygen. So this also helps us with our covalence numbers. So let's check now. We'll do our three check here. We're going to check for valence electrons. 2, 4, 6, 8, 10, 12. Valence electrons is 12. Okay, valence electrons we checked. Covalence number. Okay, for hydrogen, covalence number is 1. Okay, covalence number is good right here. We checked the valence electrons already. Check covalence number 1. Is carbon making 4 bonds? 1, 2, and then 3, 4. 2 in the double bond. 4 bonds altogether. Yes, carbon is obeying its covalent number. Valence number. Is oxygen making 2 bonds? 1, 2. 2 bonds. Yes, oxygen is making 2 bonds. So its covalence number rule is obeyed. So we're good there. Finally, does everyone have an octet? Okay, except for hydrogen. Remember, hydrogen's a special case. Hydrogen's a special case. It only needs the 2 electrons. So the hydrogen, it's good with its 2 electrons. The carbon here, 2, 4, 6, 8 electrons around it, all in bonds. So yes, carbon has an octet. Finally, oxygen, 2, 4, 4 in the bonds, 6, 8, 4 more in the lone pairs. 2, 4, 6, 8. 8 electrons around the oxygen. It obeys the octet. Again, always do this check at the end, because if you check it and if all the checks work out, you're right. You already know you're right. It's pretty great, right? You don't need anyone to tell you that you're right, because you know you're right. Okay. One more example here. Oops. Why is this showing? I don't know why this was showing. Okay, well. Okay, so I'll draw the skeleton structure anyway. So let's follow our 5 steps here. Okay, remember the first step. Always count the valence electrons first. So we've got CPF, 1 carbon, 1 phosphorus, 1 fluorine. Okay, we've got 1 carbon. Let's go back to our periodic table here. So now our molecule is CPF. We've got a carbon, phosphorus, and a fluorine. So our carbon here is in group 4, so each carbon has 4 valence electrons. We've got 1 carbon with 4 valence electrons, so that's 4 valence electrons from the carbon. For covalence number, each carbon starts with 4 valence electrons. It needs 4 more to have 8, and so its covalence number is 4. We have 1 phosphorus, and phosphorus has 5 valence electrons. So 1 phosphorus with 5 valence electrons, that gives us 5 valence electrons from the phosphorus, 1 times 5. And for covalence number, the phosphorus starts with 5 valence electrons. It needs 1, 2, 3 more to have 8. And so covalence number is 3 for the phosphorus. Next, we have 1 fluorine. Fluorine is group number 7, so it has 7 valence electrons. And the total number of valence electrons from fluorine is 1 times 7. 7 valence electrons. Finally, for covalence number, since fluorine starts with 7 valence electrons, it would need 1 more to have 8, so covalence number is 1. Now let's add up all the valence electrons. 4 plus 5 is 9, plus 7, that's 16. 16 total valence electrons. So now we're going to make bonds, and I'm going to draw this up here. So I'm going to put this carbon in the middle because it has the highest covalence number. So that's step 3, draw the skeleton. We put carbon in the middle since it has the highest covalence number. And then we're going to put phosphorus and fluorine on the outside. Okay, so that's the end of step 3. We've drawn a skeleton. Now we put electrons around the outside atoms first until we run out of valence electrons. So we've got 2, 4 down so far. So if I put lone pair here, that will make it 6. So 2, 4, 6. 8, 10, 12, 14, 16. That's all of the electrons I have. I've run out of electrons here. Okay, but notice carbon does not have an octet. So we started with 2 bonds. Those are 4 electrons. Then we do 12 more, 2, 4, 6, 8, 10, 12, to give the fluorine and the phosphorus an octet. We always do the outside atoms first, and this is why. It's because when we run out and we go to make a double or triple bond, we're going to be sharing inward, which is a lot easier to figure out than sharing outward from the middle. The middle could share in all kinds of directions, but inward is only sharing towards the middle atom. And so that's why we always, in step 4, write the lone pairs on the outside atoms first. Okay, so next what we're going to have to do is we're going to have to figure out a way to share so we can get the carbon to have an octet. So we're going to move on to step 5. Only because we've run out of valence electrons, that's the only time we use step 5 and make double or triple bonds. But since we ran out of valence electrons, we're going to now share. So the question is, which atom are we going to erase its lone pair and turn it into a double bond? The fluorine or the phosphorus? And this is where it's a really good idea to look at your covalence numbers. So clearly, these do not all have the right number of bonds. Carbon would like to have 4 bonds, but right now it only has 2. It's about to get more, though, when we make a double bond or a triple bond. Fluorine, however, phosphorus would like to have 3 bonds. It only has 1. Fluorine would like to have 1 bond, and it does have 1 bond. So what this tells you is that since fluorine has 1 bond, it's not likely to make a double bond. So we should not be sharing from the fluorine to make a double bond. So that's another thing that the covalence numbers are really useful for. Besides letting you know which atom to put in the middle, they also tell you where you should make your double or triple bonds. Because if an atom like fluorine wants 1 bond and already has 1 bond, well, then you shouldn't make a double bond to it or a triple bond. However, the phosphorus here, could have more bonds. So what we're going to do is we're going to erase the lone pair from the phosphorus, and we're going to make that into a double bond. And so we've done it there. Okay, the problem is carbon still does not have an octet. The number of electrons around carbon is 2, 4, 6. Only 6. That's not 8. So what we're going to do now is we're going to share one more time because we're still out of electrons. Let's count them. 2, 4, 6, 8, 10, 12, 14, 16. We've got 16 down. We can't put any more down. What we've got to do is we've got to move some. So we're going to move another lone pair off the phosphorus. And we're going to share that with the carbon in what's known as a triple bond. And now it looks like we have got an octet. So it's written right here too. So this is our skeleton, and this is what I had before. We had the carbon without an octet, and we shared the electrons inward. So this is what I ultimately drew. And I want you to notice something. Let's go back. Did you notice that this skeleton has like a bend in it, but this one is a straight line? The truth is that neither of these represents the real shape of the molecule. The Lewis structure is not meant to necessarily tell you the real shape. It's meant to just figure out what atoms are bonded to what other atoms and how. So ultimately we get carbon triple bonded to phosphorus, also bonded to fluorine. And it's true whether I draw it this way or whether I draw it this way. Either way, it's true. And these represent the same Lewis structure. Okay. So I've purposely drawn these for you in a different way on the slides and what I did by drawing them to show you that it doesn't matter the orientation. What matters is what bond is connected to what other bond, what atom is connected to what other atom. That's what matters. And so now, so we made the triple bond. This gives us 4 bonds on the carbon and 3 on the phosphorus. Let's go ahead and thoroughly check this here. So we're going to check for valence electrons, we're going to check for covalence number, and we're going to check for octet. You should always do these 3 checks so you can know you're right 100%. So we should have 16 valence electrons, so let's count them. 2, 4, 6, 8, 10, 12, 14, 16. 16 valence electrons. Yes. Okay. Next, covalence numbers. Is carbon making 4 bonds? 1, 2, 3. 3 in the triple bond and 1 in this single bond. That's 4 bonds. Good. Is phosphorus making 3 bonds? 1, 2, 3 in the triple bond? Yes. Is fluorine making 1 bond? Yes. Okay, so our covalence numbers are good. Finally, does everyone have an octet? Phosphorus has 2, 4, 6, 8 electrons around it. 6 in these 3 bonds and 2 more. Phosphorus has an octet. For carbon, it has 2, 4, 6, 8 electrons around it. 6 electrons in the triple bond and 2 electrons in this bond right here. So 8. Fluorine has 2, 4, 6, 8 electrons around it. 2 in this bond and 6 more in the lone pair. So 8 altogether. And so it has an octet. So again, if you can do these 3 checks and they work out for the structure you've drawn, your structure is correct. Okay. That said, make sure you're using a pencil when you do these. You've seen that I did some erasing. It's always good idea to use a pencil on your chemistry homework. So now that valence electrons, covalence number, and octet are all correct, we have a good structure. So now what I want to do is expand upon what I've shown you a little bit with a few more examples, just to show you what are some other possibilities out there. Again, no matter what you do, you can, if you use those 5 steps, you can always get to the correct answer. So use those 5 steps. Don't skip counting the valence electrons. Let's do each one of these here. I'll start with POF. So POF, it's got 1 phosphorus, it's got 1 oxygen, and it's got 1 fluorine. Let's get our valence electrons, let's get our covalence number. Okay. So we're doing POF here. Phosphorus, oxygen, fluorine. So we have 1 phosphorus, it's group 5, so 5 valence electrons. So 1 times 5, that's 5. And covalence number for phosphorus is how many a phosphorus atom would need to have 8. How many more? It starts with 5, so it would need 3 more to have 8. Oxygen is in group 6. It has 6 valence electrons, and it would need 2 more to have 8. So the oxygen has 6 valence electrons. Its covalence number is 2, and the total number of valence electrons from oxygen is 1 times 6. That's 6. And then we've got fluorine. Fluorine is group 7, so it starts with 7 valence electrons, and it would need 1 more to have 8. So its covalence number will be 1. There's 1, and then 1 fluorine times 7 electrons in that fluorine is 7. And our total is going to be 13 plus 5, that's 18 electrons total. So now we're going to draw a skeleton structure. That's step 3. So in our skeleton structure, we put the atom with the greatest covalence number in the middle. That's going to be phosphorus. So phosphorus is going to go in the middle. And then I just draw the fluorine and the oxygen connected to it. Again, it doesn't matter where I put them as long as the Fluorine is connected and bonded to the phosphorus, and so is the oxygen. Doesn't matter if I put it up here or to the side or whatever, as long as there's a connection between the phosphorus and the fluorine and a connection between the phosphorus and the oxygen. Okay, and so now we've got in our bonds, we've put down 4 electrons, so I could just subtract these really quick, -4. So we've got 14 left there. So I'm going to start putting them as lone pairs around the outside atoms first, not the phosphorus, but the outside, until they have an octet. So oxygen here, it's going to be, it's got 2, 4, 6, 8, 8 total. 2, 4, 6, 8. Okay. Now I'm going to put lone pairs around the fluorine until it has an octet. So like that, and now it has 8. 2, 4, 6, 8. Now it's a good idea to count our electrons that we have down right now. We have 2, 4, 6, 8, 10, 12, 14, 16. We've put 16 down, and we have 2 more left to put down. Those 2 can now go on the phosphorus. But we do have an issue, and our issue is that the phosphorus does not have an octet. It only has 2, 4, 6 electrons around it. So that means we're going to have to make a double bond. And so when we make the double bond and we decide whether we're going to share oxygen's electrons or fluorine's electrons, we should look at the covalence number. The covalence number for fluorine is 1. It only wants to make 1 bond. It's already making 1 bond. So we should not make a double bond here. Instead, we should use the electrons from the oxygen to make the double bond. And so we're going to erase this lone pair, and now we're going to instead make it a double bond. Okay, so it's looking like we might be done. So let's do our checks here. So we're going to check for the number of valence electrons. We're going to check for the covalence number. We're going to check that everyone has an octet. So let's double check that we have 18 valence electrons total. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, we have 18 valence electrons total. Covalence number is phosphorus making 3 bonds. Valence number 3. 1, 2, 3. Yes. Is is oxygen making 2 bonds? 1, 2. Yes. Is fluorine making 1 bond? Yes. Okay. So covalence numbers are good. Valence electrons are good. Finally, octet. How many electrons are on the oxygen? 2, 4, 6, and 8. Good. How about the phosphorus? 2, 4, 6, 8. Good. Now how about the fluorine? 2, 4, 6, and 8. Good. They all have 8. They all have an octet. So our structure here is good. Okay, next, we have a rather large molecule. So that can happen. You can have really big molecules, and then it can become hard to figure out how you want to write your skeleton. In fact, when a molecule is large, there can often be more than one correct way to write it. So you have to do a little bit of guessing. Okay, so in this molecule, we have 3 carbons, we have 9 hydrogens, and we have 1 phosphorus. So our atoms here are carbon, phosphorus, and hydrogen. Okay. So carbon has 4 valence electrons, phosphorus has 5, hydrogen has 1. So 4 valence electrons for each carbon, 1 for each hydrogen, and 5 for each phosphorus. So from the carbon, we have 3 carbon atoms, each has 4 valence electrons. So the number of total valence electrons from carbon is 3 times 4, that's 12. For hydrogen, we have 9 hydrogens, each has 1 valence electron, and so the total valence electrons from the hydrogen are 9 times 1, which is 9. And then we have 1 phosphorus, it has 5 valence electrons, 1 times 5. So now we add these together and we get 26 total valence electrons. In terms of covalence number, carbon starts with 4 valence electrons, it needs 4 more to have 8. So that's going to be a covalence number of 4 for the carbon. Hydrogen, it's always covalence number 1. That's special for hydrogen. And then phosphorus, it's group number 5, needs 3 more to have 8. And so its covalence number is 3. And so now we've got a large molecule, so we're going to have a situation that can happen with big molecules. You'll have more than one center atom. And so what you're going to want to do is put the center atoms in the middle, but put the one with the highest covalence number more in the middle, basically. It won't always be there, but it does help you with your guessing. So for example, we have 3 carbon atoms, so I'm going to put them all in the middle, connected to one another like this. Okay. And then the phosphorus atom, I could put it connected to the carbon. I could put it on the side. Like I said, there's lots of different ways that you could draw one like this. I'll just put it right here. So I meant to make this red, by the way. So carbon, carbon, carbon. And then the phosphorus, I can put it attached to the middle carbon or to the side. Either one of those would work. But notice I've put it more to the outside because it wants to make less bonds. So it's most likely to be on the outside. Okay. Now I've put my 3 carbons down and I put my 1 phosphorus. It's always a good idea to put hydrogens last because the hydrogens, all they can do is make 1 bond. So they have to be on the outside. So we're going to start to put our hydrogens down. Now let's say I start putting my hydrogens down on the phosphorus. Hydrogen here and a hydrogen here. When I'm deciding where to put my hydrogens, it's a good idea again to look at the covalence number. It's always a good idea to look at the covalence number when you're drawing your skeleton, because then you can know how many bonds this atom is likely to make. Phosphorus is likely to make 3 bonds, and if I put 2 hydrogens on it, it's already making 3 bonds. So I probably don't want to put another hydrogen on it, because then it will be making 4 bonds, which is too many. The carbons, however, they do want to make 4 bonds. So if I put 2 more hydrogens here on this one, then this carbon is making 4 bonds. 1 to the phosphorus, 1 to the carbon, and then 2 to hydrogens. So now I've put down 4 hydrogens, but I have 5 more left because there's 9 hydrogens total. So this will be my 5th one, this will be my 6th hydrogen, and then this carbon now has 4 bonds, so it's full. And then this carbon could take some more, so I'll just fill it up with bonds. Now this carbon has 4 bonds too. So it's always a good idea, again, to look at the covalence number so you know how many bonds to make to an atom. Now all these carbon atoms have 4 bonds. And now let's look at my number of hydrogens. Did I put down 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, I did. Okay, and so now I've got a skeleton. And so now it would probably be a good idea to see, well, how many valence electrons have I put? So I have 20 something, let's count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have placed down 24 electrons in bonds. So that means that I've got 2 left. And so I should put them on an atom that wants an octet. Remember, hydrogen is always full with 2. So you never ever put lone pairs on hydrogens. Don't put lone pairs on hydrogens. I'll cry on my computer screen. Hydrogens are full with 2 electrons. Don't put them there. Next, well, can we put them on the carbon? No, the carbons already have 4 bonds. They already have an octet. The only atom that's lacking an octet that needs one still is the phosphorus. It has 2, 4, 6 electrons around it. So my lone pair should now go on that one. And now it looks like I've put down all of my electrons. So it seems like it might be the structure. Let's check. Again, always a good idea to check at the end. Then you can feel confident that you're done. So total number of valence electrons, we should have 26. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have 26. Great. Our valence electrons are good. Covalence number. Is each carbon making 4 bonds? This carbon is making 1, 2, 3, 4 bonds. Cool. This carbon is making 1, 2, 3, 4 bonds. Great. This carbon is making 1, 2, 3, 4 bonds. Good. Every carbon is making 4 bonds. Is every hydrogen making 1 bond? 1 bond here, 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 and here. Yes. Every carbon is making 1 bond, or hydrogen rather. Is every phosphorus making, is the one phosphorus rather, making 3 bonds? 1, 2, 3. Yes, the one phosphorus is making 3 bonds. Okay, so our covalence number rules are obeyed. Now, does every atom have an octet? With the exception of hydrogen, right? Hydrogen should only have 1 bond and that's it, no lone pairs. So we already checked. All these hydrogens are making their 1 bond. They are good. Does this carbon have an octet? 2, 4, 6, 8. Yes. Does this carbon have an octet? 2, 4, 6, 8. Yes. Does this carbon have an octet? 2, 4, 6, 8. Yes. Does this phosphorus have an octet? 2, 4, 6, and 8. Yes. We are good. Okay. And now finally, what about the last one? The last one is a bit tricky. K2S. Now what I've shown you here in this whole lecture is all of the 5 steps for how to write the Lewis structure for a covalent molecule. But K2S is not a covalent molecule. How can I tell? Potassium is a metal. This is ionic. This is not covalent. And so the way you would write the Lewis structure is the ionic way. Now, admittedly, drawing ionic Lewis structures is not very useful, except for when I explain to you how ionic compounds work. But other than that, they don't do a whole lot else for you. What we're going to find, though, is that molecular Lewis structures for covalent molecules, these can do a lot for you. They can tell you the shape of the molecule. But covalent, Lewis structures for ionic compounds don't tell you a lot. If we start with potassium, potassium is group 1 here. It has 1 dot. We've got 2 of them, each with 1 dot. Then sulfur. Sulfur is group 7. Or sorry, group 6 rather. So 6 dots just to show you here. Potassium, group 1. Sulfur, group 6. So what happens when the ionic compound is made? The potassium gives each potassium gives 1 valence electron, so you end up with a plus, and then the sulfide ion. So these These potassiums are +1 because each one lost an electron. The sulfur gained 2 additional electrons, these ones here, along with the 6 it already had. So its charge is -2, and this is the Lewis structure. That's the way you write it for an ionic compound. Again, not very useful because ions just all stick to one another in a big chunk. So this doesn't really tell us about the way that they stick together. It doesn't tell us a whole lot of anything. Whereas Lewis structures for molecules, they tell us which atoms are bonded to which other atoms, which is really useful. And so this was just to keep you on your toes and to make sure that you're remembering the difference between an ionic and covalent compound, and that they bond in completely different ways. And so keep that in mind. And so that's the end of the lecture on how to draw Lewis structures. This is going to take you a lot of practice. We're going to be practicing this week. We're also going to be practicing next week as we further use those Lewis structures. And in the next lecture, there are only 2 this week. In the next lecture, though, I'm going to show you basically what we can do with these Lewis structures after we've got them, how we can determine the shape of a molecule using the Lewis structures. So I'll see you in the next video.